Hello, and welcome to this video explaining the basics of triple integrals. So to begin with, in double integrals, if you recall, we took the function over an area from the xy plane where we were doing box shapes where it was a space in the xy plane times the function as a height above. With triple integrals, there isn't a simple geometric representation because now we are taking sections of a three-dimensional space with the integral. For the integral, typically we have dz, dy, dx, which translates to what you could think of as being cubes that are some amount of space in the x-axis, some amount of space in the y-axis, some amount of space on the z-axis. The function itself is a fourth dimension. So for that reason, there isn't as easy of a way to visualize triple integrals. However, it is worth noting that to approximate them, you can add up the function times either a cube or another box shape from the x, y, and z axis and add these together. There just is not a simple geometric representation. Double integrals. With triple integrals, we can place the limits for z, y, and x as individual integrals with the functions and then the differentials. To integrate, we will integrate with respect to one variable first, then the next variable, and then finally the third variable. Doing so will result in a number as the result of an integral. Example of a triple integral, consider the triple integral with respect to b, which represents, in this case, b stands for box, although you could call it whatever you want, of the function x cubed y plus 8 square root z dv. By the way, please note that dv in this case is referencing the volume of a small box that we are then multiplying by whatever value the function has. In doing this integral, we first of all can place each of the limits for each variable into one of the integrals. So in this case, I am choosing to place the limits for x in the inner function, then the limits for y in the middle integral, and the limits for z in the outer integral. Based on this choice, I start out by integrating with respect to x. So the antiderivative of x to the third is 1/4 x to the fourth. Since no other values involving x are there, and since everything is being multiplied, the resulting antiderivative is 1/4 x to the fourth times parentheses y plus 8 times square root z. And I will be evaluating this at x equals 1 and x equals 2. And as usual, I will be subtracting this. Doing this evaluation and subtracting results in 15/4 times parentheses y plus 8 times square root z dy dz. Going with the next layer, I have dy. So I'm going to take the antiderivative of y plus 8, noting that everything else is being multiplied and does not involve y. Doing so results in 15/4 times parentheses 1/2 y squared plus 8y parentheses times square root z evaluated from y equals -7 to y equals -5. Again, I plug in these values for y and then simplify to get the integral from 0 to 9 of 4z to the 1/2, noting that the square root of z is z to the 1/2 dz. At this point, it's a single integral. We can take the antiderivative, or by the way, as I've said you can use Desmos at this point. Either way, if I take the antiderivative, I get 8/3 z to the 3/2 evaluated from z equals 0 to z equals 9, which gives 72. This is then the result of a triple integral. The key point here is that a triple integral is very similar to a double integral, just that there's that additional step. And as a matter of fact, when it comes down to just about everything else, once you've mastered the way of doing double integrals, integrals of any dimension, be it 3, 4, or higher, really are the same process. By the way, typically triple integrals are the highest that most of the scientists go to. Occasionally you might see a quadruple integral, mainly because typically the dimensions are x, y, and z for the physical dimensions, with possibly time as a fourth dimension. Either way, this is the general process. You may have noticed that a generic triple integral has dv as the initial differential. And yes, similar to how double integrals have dA as the initial differential, and we were able to use double integrals to calculate area, with a triple integral and with dv as the initial integral, we can use triple integrals to calculate the volume of a solid if we know the equations of the surfaces. As a demonstration of this, let's set up a triple integral to calculate the volume formed from the solid that results in the intersection of the paraboloid z equals 25 minus x squared minus y squared and the plane z equals negative 24. Before we can set up the triple integral, we need to have the lower and upper bounds for x and y. Because by the way, the lower and upper bounds for z are already present in the problem. We have z equals negative 24 as a lower bound, and z equals 25 minus x squared minus y squared as an upper bound. To calculate the bounds for x and y, we set each of the surfaces equal to each other, because we know that if we replace z with negative 24 in the initial equation, z will be eliminated, and then we will be able to form an equation involving only x and y. Doing so yields the equation x squared plus y squared equals 49. You may recognize this as a circle. We can solve it for y to get lower and upper bounds of negative square root 49 minus x squared and positive square root 49 minus x squared for y. For x, because it's a circle and because 49 is equal to 7 squared, the lower and upper bounds for x are negative 7 and 7. This gives us our triple integral. We note that similar to double integrals, the outer integral for triple integral must contain only numbers. An additional item that needs to be met with triple integrals is that the middle integral must not include the variable that we already integrated for in the first integral. In this case, dz is the innermost integral. That means that the middle integral must not include z. And similar to double integrals, the outer integral must only include numbers. And this is a summary of how to use triple integrals to calculate volume. Another thing that we can do with triple integrals is take the triple integral over a region that's bounded by surfaces. For this example, let's consider the triple integral over a region that is bounded by the paraboloid z equals 64 minus x squared minus y squared, the positive xy plane, the positive yz plane, and the positive xz plane. To begin with, note that the positive xy plane means z equals 0 and above. So our limits for z will be 0 to 64 minus x squared minus y squared. This also means that we will be looking at a portion of the circle x squared plus y squared equals 64 for x and y. Now, we know the positive yz plane means x is greater than or equal to 0, and the positive xz plane means y is greater than or equal to 0. Combining this along with ideas from circles from the last slide, we get the triple integral with bounds 0 to 64 minus x squared minus y squared dz, 0 to square root 64 minus x squared dy, and 0 to 8 dx. From this point, we take antiderivatives like we normally would. We also note that this function does not have z in it. For that reason, we take the antiderivative of x cubed y dz, we end up with x cubed times y times z, which is then evaluated between z equals 0 and z equals 64 minus x squared minus y squared. Substituting these values and subtracting, well, we know that subtracting 0 really is trivial, we get the integral from 0 to 8, integral 0 to square root 64 minus x squared of 64x cubed y minus x to the 5th y minus x cubed y cubed dy dx. We then take an antiderivative with respect to y, since dy is next, which results in 32x cubed y squared minus 1/2 x to the 5th y squared minus 1/4 x cubed y to the 4th, evaluated from y equals 0 to y equals square root 64 minus x squared. We can then plug in, which will result in the integral from 0 to 8, 32x cubed times 64 minus x squared minus 1/2 x to the 5th times 64 minus x squared minus 1/4 x to the 3rd times 64 minus x squared raised to the 4th. At this point, we could do this integral by hand. It would take a considerable amount of time, since all that would really need to be done would be distributing and multiplying these out and then taking antiderivatives. Similarly, we could also use Desmos. Either way, at this point, we have done the operations for this integral that are beyond anything we had done previously in this course. So we will stop there. Thank you for watching this video. I hope this gives you a better understanding of triple integrals.